some of the scientific stuff. But that didn't go on too long. He only had a couple of days to do that. And then they had to shut down for the night. And normally, just like the Nova Sea lander, they don't really design the electronics to survive the night. It's just too cold. It would cost way too much to really try to do that.
And the lunar night lasts
14. It's 14 Earth days, yeah. So, you're not going to ride that out very easily. But it did actually manage to restart the next lunar afternoon. They actually had enough power. And in fact, they actually had too much heat. For some reason, they actually had too much. And so they had to be very, very careful not to overheat the equipment. But one of their main scientific instruments, the multiband spectroscopic camera, which they use for analyzing the rocks and the dirt and everything, that one apparently failed. But they're still able to get pictures and some of the other data. So it's not functioning very well, but they managed to actually run even after living through one of those nights. And now they had to shut down again. And the next window they'll have is in March, and they'll get a few days. My guess is it'll be kind of zombie-like. Maybe you'll be able to communicate with it, maybe not, but it won't be very intelligible. That's just a guess. Think zombies.
All this demonstrates that getting to the moon isn't easy. It still remains a challenge.
So my clicker doesn't seem to be working here. What? Oh no, recording has stopped. All right. Okay, we're back. All right, so getting near the end here. Another topic that we've covered in a lot of our previous meetings is basically the orbital debris problem, and most people have heard about this. There's a lot of satellites up there. There's dead ones. There's all the upper stages that got those satellites there. Many of them are still there. There's pieces of stuff that were blown up in anti-satellite weapons testing, just all kinds of stuff up there. I found this picture, which is kind of a nice one from the United Launch Alliance, just kind of highlighting the problem that as you're close to Earth, the low Earth orbits, like where the International Space Station are, they're like 400 or 500 kilometers, that kind of a range. And basically, satellites that are orbiting in that area, they can last in terms of years, 3 years, 10 years, somewhere in that range, depending on the altitude. And the reason is there's still enough air molecules up there that you get some friction. And over time, it gradually drags you down. But you don't have to get up much higher before you're off in the land where it takes centuries or even thousands of years. The ones that those big old satellites that were used for satellite transmissions for television and that sort of thing, they're up in geosynchronous orbit 22,000 miles up. Those things will be there forever without special heat treatment. When they die, what they're supposed to do is raise those up even further to what's called the graveyard orbit. It's highlighted there on that picture. So anyway, that's highlighting the problem areas. So in a way, most of the congestion is down in low Earth orbit, but the good thing is that cleans itself out after a while anyway. But there's still enough of it that it's gotten to be a concern. So the reason we're talking about this is Astroscale, a Japanese company, has just launched something to do something about that. They're going to try to remove some, or at least they're going to study it. There is a dead upper rocket stage up there. It's H2A. It was a Japanese upper stage. It was launched back in 2009. That's the same model of rocket that took that slim lander, to the moon. 11 meters long, 4 meters in diameter, and weighs 3 tons. So it's a big chunk of metal that's up there. There's no communications possible with it. It's not powered. It isn't like you can tell it to move around. It's just dead. It's just up there. It wasn't prepared ahead of time. Some of the solution methods for dealing with space debris have said, well, okay, let's put special markings on things so we can identify, places to dock or places to at least identify what it is. But none of that was done with this old stuff. So this is an attempt to figure out what to do with the old stuff. The biggest problem in all these things is they might be spinning. And if they're spinning, it's pretty hard to just grab it, which is what you're going to want to do. You're going to grab it. Whatever craft you're in is going to start spinning too, and you may easily lose control. So anyway, there's this Astroscale is the company. It's a joint project with the Japanese NASA, JAXA. It's a commercial removal of debris demo. What they're going to do is they're going to launch, and they're going to, as they approach it, you can see in this picture here, the smaller one is the satellite they're sending up. It is actually quite a bit smaller than the rocket they're looking at. But all they're going to do is come near it. They're going to try to match the orbit and then actually circle around it multiple times and make sure that they can really get a good understanding, in particular to be able to show that you can match at least the primary axis of rotation, which is, if you can do that, you've probably got a better shot at handling it after that. This is only doing the observation. It's not actually doing any of the debris capture. It's not doing anything with it. They're just proving you can even do that. All these things are all, baby steps, if you will. They haven't even contracted the next step, which is try to actually get this thing. But that's obviously what the intention is. The intention is to then grab this thing. Okay. Well, that's the biggest piece of debris up there. Yeah, that's huge, and that's big. That's such a whole controversy in itself. I can hardly even talk about that. But yeah, I mean, some people want to try to save it as a museum. Some people want to, dismantle it. The obvious thing long term, which I'd really like to have, is a circular economy where you simply melt down this stuff and build new things up there and never have it come back to Earth. Because even if it comes back to Earth, if it, the pieces, first of all, some of it will just evaporate in the atmosphere, but maybe that's not such a great thing. Do you really want to be breathing in aluminum ions? It's not necessarily a good thing. Anyway, so moving on though, Varda Space, we talked about them in November. And what they're doing is manufacturing in space, but this is manufacturing where you launch essentially a small lab that does crystallization kinds of things, in this case for biopharmaceuticals. It goes up, you do it, and the reason you do that is that you can make much better crystals in space where there's no gravity, microgravity. You can make much purer components, do a lot of different things you can't do on Earth. And so they did this. They sent one up in June. It took them about 3 weeks to make the drug they were trying to make, and then they weren't allowed to land. And so that was back in, they launched it in June. They were done by July, and they were waiting around. Finally, just this month, the FAA granted a re-entry license for these people. Now, they also had to get approval from, there's a military range in Utah where they were landing, and they had to get approvals there. All that stuff took time, but they finally got it, and then a week later they landed. We don't know the results yet, because there's several kinds of results. One is they're sending the drug out to an independent testing lab to verify that it's the good stuff, no bad things happened. The other thing, they're actually making money. The Air Force is paying for information. They want to know more about hypersonic reentry. Things flying at 25 times the speed of sound when it's coming in. And so that's the Air Force wants that information. We'll probably never know what they find out, but we will find out about the drugs. Yeah. Well, apparently it was used for HIV treatments, and also actually it's a part of Paxlovid, which is used for treating COVID. Yeah, Paxlovid is a combination of ritonavir and some other drug, whatever it is. So the thing is, these are expensive drugs. Obviously, if you're not going to make aspirin in space, it still costs you a lot of money to get up there and down. In their case, they send it up. You can see that kind of on the left-hand side here. This little thing here, this is in the middle, for instance, that's really the lab. And they just basically, they have a heat shield which heats up, and then eventually a parachute that drops, and they're landing on the land.
So basically, this is a pharmaceutical manufacturing product line factory.
Yeah, and it's not a big one. You can see that from the picture. This is the recovery right here. But the point is they can reuse this thing, and they can get them up pretty quickly. So obviously they're going to start small scale. They want to get to the point where at least they fill up a Falcon 9, at a time. But for now, you start small because it doesn't cost as much. So here you're still demonstrating feasibility. They're doing another launch this year. There's a test. I think the third test they're hoping for this year, they're actually hoping to go commercial with it. And some of that will be landing on Australia. They have so much trouble getting approvals from the US that they're going to land on Australia. They still need the FAA approval from the US because they're a US company, but at least they won't have any problem, landing on a military test range.
You didn't thought the notion of or launching that they find out 5 places and permission to land at 5.
Well, you might think they would have worked all that out, but something went awry in that whole process. Who knows? We'll never know the story on that. Okay, pop quiz time. Can you guess the country and the rocket? Now I blotted out some of the markings, logos and stuff, so you won't. You can try squinting, but I don't think you're going to find any identifying names on there. Any guesses? Oh, you always know these things. Does anybody else know what this is? Okay, go ahead. You can say it.
I'm guessing Mars, planet, Long Island?
No. Actually, this is Japan. This is the Taganashima or something. It's an offshore island of Japan. This is a launch. This is actually the H3, which is the new rocket replacing the one that just took that Slim lander up there. Built. This is still basically being owned by their NASA, built by Mitsubishi. They launched on February 16th. That was their first success. They had one previous launch that failed. Now, one thing that's kind of sad about this whole thing is that, yeah, it's basically competing with the Falcon 9 and the Vulcan, which is the United Launch Alliance thing that just launched this year for the first time. It's expendable only. So basically, what they're doing is they're competing with the Falcon, the Falcon 9, as it existed around 2010. They're finally competing with the 2010 version of the Falcon 9, not the 2015 version, which was when they started doing reusing for the booster. And that's when things really started to get cheaper for SpaceX, is by reusing the equipment, they can get the cost down. They can't do it. On the other hand, this thing is quite flexible. They can have either 2 or 3 engines. They're hydrogen and liquid oxygen. And they can have 0, 2, or 4 solid rocket boosters. This particular one has, they're little ones down here on the bottom. You can see them, the little teardrop kind of things there. Anyway, this is the first success. So they're at least having something. They're managing to keep their rocket scientists employed. Okay, the last one.
The thing about the Japanese space program is that they come up with products that work. It tends to take them a long time to develop them, and they tend to be extremely expensive compared to everyone else's.
Well, this actually, they think that they can probably get pretty competitive with, strangely enough, with the Falcon 9. This won't be that much more expensive. I don't know why, actually, to be honest.
This represents really a huge step for
it is.
The Japanese. Huge improvement.
Yeah. On the other hand, I wouldn't laugh at them too much, because they've done some of the best exotic kind of, spacecraft. I mean, they're the ones that did the first recovery mission to sample an asteroid and bring it back. So they've done quite a few things with these kinds of launchers. Okay, this is the last pop quiz item. Okay, country and rocket. Okay. This is what? Oh, and the last one? Yeah, they are. Yeah. I don't know where they get their hydrogen. Is it green? You're asking, is it green or electrolysis or,
There's that big body of water behind it. So that's
well, yeah, they do have water, but unfortunately that's loaded up with salt, which you electrolyze that, you get a lot of chlorine gas. But,
the reason why I asked is some of the and the sources of electricity, and up to 32 hydrogen stable.
Oh. Oh. This is, I don't know where they get it from, but this is just straight up liquid hydrogen, however they get it. Yeah.
According to the aviation, I believe it was regular commercial liquid hydrogen, old style, traditional style. We'll see at what the Japanese try and upgrade.
Anyway, these things will never be reusable. They have the same problem that the Vulcan has, the ULA one, which is that if you only have a couple of engines, you can't land the booster because it's too powerful. Basically, as soon as you turn it on, it just goes shooting right back up. So, it will always be expendable, meaning it will always be more expensive. Okay, this one, I guess I didn't get any takers on this.
Oh, it's China. India. Long march.
Okay. Oh, you cheated. You looked at my next slide, did you?
Well,
okay.
I just popped up.
On March 7th? It's not China?
It's not China.
Well, he says it's not China.
Well, you're right.
All right.
I don't think it's Indian.
It's Indian. This is one. It's called GSLV. They don't have great names, but anyway, they are a geosynchronous satellite launch vehicle. This thing is, yeah, you were right. It wasn't China. This one's actually, they've had this since 2001. This is a pretty old rocket. This is not a new thing, but it just had a recent launch. They launched a big weather satellite, so that's why I put this in here. This is actually 3 stages, solid. It has a hydrazine liquid stage, which immediately think, okay, think toxic, horrible, you hate to be there. That's sort of left over. They got a lot of their early training. They pretty much picked up Russian technology, and the Russians always used hydrogen. Well, actually, so did we. Actually, everybody did. But they kind of were in the Russian school of doing things, and that rocket was old, so they're still doing it. At some point, they will replace this. They are working on replacements. Okay. Finally, we always ask at the end, how many launches have there been since our last meeting, which is about a month? Just take a guess. And by the way, this is the launch of that lunar lander on February 15th. So any guesses as to how many launches there were in the last month? Okay.
26.
Okay, that's a guess.
20.
You're a lot closer. Okay, the answer is 13 plus 4, 17. Actually, it's a little slow.
Oh, wow.
Yeah. That's funny to think about that. You go back a couple of years to think that 17 launches in a month is slow. But, actually, SpaceX even is falling behind. They were hoping for 150 launches on their own, just by themselves this year. They're going to have to launch like 3 a week to keep up, if they want to meet that target. They might not quite make it.
Yeah, they got 96 last.
Yeah. So this is really just, we can't go through all these, but gives you an idea of the kinds of things that are going on. There's a lot of satellites going up for communications. We've already talked about some of like the Japanese, they had the test flight. We talked about the commercial removal of debris launch. And interestingly, that's not an Electron rocket, which is a very small one. But, they figured that was enough. Yeah, I don't think I'll go through most of these. Crew to the International Space Station. We have these consolidated loads. SpaceX periodically launches a rocket that just includes a lot of payloads. They just basically bundled up. In fact, they don't even do the bundling anymore. There's third parties that come in and they will sell you a slot, on a SpaceX rocket, a Falcon 9, and you pay those people and they bundle it up. They take care of the launching of it. Some of them have tugs. They have space tugs. So if you don't want to go to the orbit that SpaceX is going to, you get a little tug and they'll take you out somewhere else. And there's a couple of those in there. So there's more than 53 satellites. These are just the payloads, some of which have multiple satellites in them. So I think they're one of them. Yeah. And there's a whole bunch of them. I think that's pretty much it. Yeah, that's it. Okay.
And we probably should move straight.
Yeah, I'm afraid we better move on fast here.
And then I'll take
Okay. Yeah, here. Oh, you still have it, right?
Yeah.
Oh.
There. Okay, the first one is Daniel talking about code to energy simulating nuclear fusion. That's a good point. Okay, so about a month ago, yeah, it's right here. Oh, got it. I just have to. What is the Nova spotlight? So about a month ago, there was a science and engineering fair, and there was high school projects and half of which were middle school projects. And the science and engineering fair is an Alice organization like Good job. Aaron, am I not being is it muted? Oh, there we go. And we have two microphones. So that makes
Yeah,
it.
get the other one.
Oh, excellent.
Yeah, I think I'm sure it's on. Yeah,
It
this
is.
is on too.
It's on too. Okay, excellent. And this.
So the actual microphone is on top of this thing. So just if you attach it to your vest or something, as long as you're generally pointing anywhere remotely resembling up.
And this is a group project by Daniel and Silas. And so we have both of them here today. And
put it in your shirt pocket or something. Get it.
Okay. Can we stand like over here?
Yeah,
Okay.
yeah, off to the side there, big time, and obviously the panel so that people around can see you.
Okay. So for many, many years, decades, there has been this effort to find a renewable and yet very powerful source of energy. And recently there has been breakthroughs in a very particular field known as nuclear fusion. So we'd like to talk about what we've done for that category and how our project could benefit you all. So nuclear fusion is not without its risks. It is the same process that forms the immensely destructive hydrogen bombs, which have never been used in war but are even more powerful than the two that were used in World War II. So they're extremely lethal and cause mass destruction when something goes wrong. So that got us thinking, how could we make it safer to use or find some way to make it more reliable? So we explored nuclear fusion and how you could make this fusion reactors to combine the energy but keep it controlled so that the energy goes towards energy production and not destruction. And there's recently been breakthroughs, such as one in Livermore, where they had a fusion reaction that actually produced more energy than went in. So upon starting our project, we asked the question, is it possible to simulate nuclear fusion in some sort of free web application or any way that would be accessible to the general public? And that led us to our hypothesis. If such a program existed, it could yield valuable and dependable data for the greater scientific community. So we split the project into two parts. I focused a lot more on physics, and Saz focused a lot more on computer science. So I'll go first. I did a very deep dive into physics, and I got to three important equations that I'd like to discuss. The first of which is binding energy. That's the energy that holds the nucleus together, the nucleus of the atom. And its equation to solve for how much energy it is the amount of protons times the mass of the protons in AMUs plus the amount of neutrons times the mass of neutrons in AMUs minus the total number of protons and neutrons. All of that times the speed of light squared is your binding energy. Then the second equation, which you can see in the middle, is the fusion energy output equation. That's precisely how much energy could be output from a fusion reaction. And that's from the mass of the reactants minus the mass of the products times the speed of light squared. And a side note is that in the third equation, you can see that if the amount of nucleons, which nucleons are just a general name for protons and neutrons, remains consistent throughout the procedure. You can rewrite the fusion energy output equation in terms of the binding energy equation. Now let's move on to the 3D engine development.
So my part was, it's kind of like is multiple parts put together. First is a 3D engine to display the simulation results. Second, a website to act as an interface. Third, like developing the code for the simulations. So to make this, we use JavaScript for the 3D engine using WebGL as a graphics framework and GL Matrix for matrix. While 3D engines already exist that we could use instead of developing our own, we decided to develop our own for, like, first of all, full control over how it works. And second, to get the experience with developing applications like this. I'm going to try and give an overview of how it kind of works. So to start, we made a triangle. We drew a triangle on the screen. And this is because everything like 3D is made up of triangles at like the most basic form. This was a lot more work than you'd expect because in order to draw this, we had to set up a lot of the rendering functions too, just to get that output. Then second, we worked on making it to support multiple objects. So the first time I actually tried to do this, I left it too late and I had to restart the project because I just got so confused by making the code support arrays of objects that I just decided to restart and like work on that portion earlier on. Step 3 was coloring. So this adds coloring to the triangles. So as you can see, that top vertice right there, that's green, the bottom two are black, and it creates a gradient between the colors. That's what's happening on the left there. So this is starting to assign values to different vertices, which is kind of like the first kind of texturing we're doing. Then step 4, that was a 3D cube. The first step is to change it from using 2D coordinates to 3D coordinates. That allows us to put the triangles in 3D, and then it's a matter of making a cube. So each face of the cube is made of 2 triangles put together, and it makes a cube. Step 5 is loading models from files. So we already have the code in place to make a model out of a set of vertices and faces. Now we just need to read that from files. So you take a file, we have to write a parser to look through the file and convert it into a form of data that can be read by the program, and then we can load models. So after that, it's textures. So for the textures, we're using texture coordinates, which are also extracted from the file. This kind of maps an image to each face on the 3D model. That's the texture we're using for the satellite. It looks really chaotic, but the coordinates map it perfectly onto the model to make something cohesive. And step 7 is lighting, which is another piece of data that's taken from the file normals. And normals are kind of like the direction a face is pointing. And using a directional light, we can kind of see the dot product, and that'll tell us how, like, in shadow each face should be. So here are a couple images that show the concepts. The left one, that shows texture mapping. Each face has a texture assigned to it from the image, and that gives you the textured box. Then lighting, there's the normals of each face, and the directional light, you just calculate the dot product. It gives you a output. So here are a couple like final steps. There's rendering. So I didn't go that much into this, but one step that like takes place is, first of all, this translation matrices, which you apply to all of the objects in the scene. This is scaling, rotation, location, all of that. Once that's done, you have kind of like a 3D representation in the computer of where everything is, and then you need to convert that to camera space. I'm using the view matrix. This like builds the scene from the perspective of the camera. Then from there, there's the projection matrix, which takes the 3D scene from the perspective of the camera and makes a 2D image. And this happens many, many times per second. So here's our final result. We can make scenes, 3D scenes. You can move around in the scenes. There's basic lighting. We also added stuff like animation. to create these scenes. And future steps would be adding stuff like shadows, making it so you can do more advanced texture things, transparent objects like glass, more smooth lighting, and stuff like normal maps. Normal maps, they're a type of texture that's used that kind of fakes like depth in a texture. So like imagine if we had a place sticking out here, it would create a shadow. And what a normal map does is it's kind of a representation of that, and it calculates the 2D shadows instead of using an actual 3D object. So it can like make objects look a lot more realistic without costing any more computing power. So these are the main equations we would use to simulate nuclear fusion. This is a work in progress project. We are not at a fusion simulation yet. Right now, we are developing the simulation engine, which is we're building something where you can just pretty much put in equations and put in a list of values for each simulation, and it'll pretty much auto create the UI for you, and you can have it going from there. So we're building the simulation engine. When we do make the fusion simulation, these are the main equations we will use. But one problem that we had while developing this is you can't just put in the equations and have it return an output for you. You have to do a bunch of kind of manipulation with the equations to make it work in a simulation. Web development. So this is the next part. 3 languages are ones we use in web development. There's JavaScript, HTML, and CSS. So HTML gives you a website that looks like Google Documents, a Microsoft Word document, just basic black text on a white screen. CSS makes it look fancy like that. It adds styling to all of it, color, positioning, everything like that. And then JavaScript makes it functional. And then simulation code. So our simulations are working, we're kind of having them, you implement the data beforehand in the UI, then you click a button to run the simulation. This will generate all the data and put it in a file. Then when you click play in the viewport, it replays that data so you can visualize it. Okay, so I can give a demonstration if you want. It's going to be a really, really basic one because it's all still in development, but hopefully it'll work out. So does this computer work?
Yes.
Okay.
Just look up on the screen.
Okay. Okay, this is going to be tricky. So I don't know if this is going to fully work. There's a 50% chance.
I'm going to type it.
Yeah. Okay, so this is our starting screen. There's a satellite we made. You can see the animation, it's spinning over time, moving up and down. There's the shadows. Well, not actually shadows, it's just lighting. If it was shadows, more of this would actually be lit. And the light is moving around. So it's lit from the bottom, not the top. And, okay.
As a
So
day-night
basic
cycle.
motion. Okay. This is really choppy and really fiddly to get working, so we'll try, but end time. Let's move that to 50. Constants, let's do negative 20, 20. And let's move this to 0.1. So this is going to be really choppy. We've not made the kind of movement smooth yet, and this is a really early version, but hopefully it should work. So you click this button up here, this generated simulation, you can click this. That downloads the data. Yeah, I can find it. But if you click that, it'll download two files. There's the like readable file. This gives you the data in order. You can read it, kind of see what's happening. There's three types of data for this one specifically. It's time, there's displacement for this current frame, and then there's the velocity change. Then there's a second version. It's just all of the data in order in a line. It's terrifying. No one can read it. But let's try and play this now. It's going to be really choppy. We've not added the animation in between frames yet. And there are definitely some bugs near the end, but let's try it. So it's slowly going to speed up over time. When it reaches the end, it's going to snap back a bit, and it's going to keep speeding up, speeding up, speeding up, 0.1 per second. You can move backwards, all the way back to the start. Yeah. Please come back.
You may want to adjust the day-night cycle to make it a little less dim.
Yeah, I need to do that. I've actually got in here in the scene part, there's a day-night cycle button here, but I've not added a like cancel animation or start animation function. You just like have to put in the animations at the start. So that's actually going to be one of the next steps. It's making it so you can cancel animations and restart them while they're running to make this work. But light color here does work. You can make it very horrifying. So this is what we've got so far. Here's what we do going forward. We improve the 3D engine, make it look just generally nicer, add more features such as shadows. And then there's the simulation code. So as you've seen, there's bugs and it's pretty choppy right now. It'll take a few more days to get that all sorted out. Then finally, we can start properly adding in all of the simulations. And to add simulations, because of all the infrastructure we've set up, it's actually really easy at this point. It's pretty much just write a function to calculate the math, place it in the program, list the values that are used, and it'll completely auto-generate all of this information here, and it can run perfectly with all of this stuff we've already set up. So we're really close to getting the simulations done. So next is the conclusion. So Daniel?
Oh, yeah. Oh, the microphone's here. Never mind. Okay. So basically, as Silas demonstrated, we found that, oh, here's the clicker. Through our like beta testing period, basically, that concepts as complicated as nuclear fusion is possible to be simulated in a web application using a 3D engine. And since the data provides reliable results because it's just based on mathematical formula, that it could likely be used to simulate actual experience before being conducted in the real world. And I just realized I can't show it because I don't have my notes, but I have a subsection that shows how you could add a scaling function to account for how much energy, like basically how efficient your equipment is, to modify how much energy output would actually occur. And then since the program can simulate it, as we showed, it could further contribute to our knowledge of understanding nuclear fusion's immense potential as an energy source. So projects like these are really important as the world continues, because as we have bigger and bigger projects, such as sending like massive infrastructure and more energy that needs to be consumed, it's very handy to have like near unlimited amount of energy in order to basically not have problems such as energy overconsumption.
Also, when this project is complete, one benefit is since it's completely free and it's accessible online, pretty much anyone can experiment with it whenever they want to, which is a really nice feature.
And yeah, adding on to that, then other people who may have like a small interest in physics or maybe don't know where to start, they could hop onto our website and be able to like they'd be able to explore the interest further and maybe make some discovery of their own.
Thank
know
you.
there's going to be some questions, but Daniel, I wanted to present you with a personalized award as well as you, Silas.
Thank you.
And we weren't able to actually give out personalized awards at the event as we went immediately from judging to handing out awards. It just wasn't practical to personalize anything, but I'm glad y'all were able to come, share your project,
Thank you.
and allow for us to give this to you. And anybody have questions? Seniors or juniors?
Or
Or
sophomores.
sophomores.
Sophomores in high school.
Yes, sir.
Very good.
Thank you.
Yes, I mean, that physics presentation is certainly what I recognize from my sophomore year in college. But, doing really well. I'm very impressed. And
Thank you.
I'm always astounded when I see how much effort it takes to have even Donkey Kong guy come over and smack someone. I mean, you definitely encountered all those problems, and
Yeah.
clearly you're learning really in detail how to deal with all that stuff and how difficult it is to make things real.
Yeah.
Gaining more appreciation for those game writers, code writers.
Greg, you had a question.
And so in the fusion simulation, what will the graphical options be? What will the colors represent? I assume it's a visualization of the fusion reaction. What
Yes.
will
Do you wanna
Okay.
explain it? Or-
Yeah, I can explain it. So what you're thinking about is where the visualization is likely going to be Bohr model atoms, but they're going to function like Schrodinger atoms. And it's going to be actually really interesting. We're going to have a lot of different visualizations like that you can see over time. One thing we're thinking about is a heat visualization. So you can visualize the heat generation and how it occurs. There'll be probably a lot of different options. There'll be like simple, just like the simple movement of the atoms. You can see more of the like interactions. It's a really hard thing to actually visualize because like you can't see where like stuff is and where it's moving at the same time. So you have to find ways to simulate that while still keeping it like cohesive, right?
So I'd like to add on to that a little bit, right? Here we kind of have what our goal is for the Bohr model, but we also encountered that superposition, which is the function when basically subatomic particles can be in multiple places at once, kind of hinders this ability. So we wanted another model, almost like an overlay, to account for that and basically have just an area, like a spherical area to show
Yeah.
where the electron could be, since we don't know exactly where it is.
So what we're thinking about now, as he said, it's kind of going to be multiple different kind of interpretations of the atom over time with different levels of scientific accuracy, because the earlier ones are much easier to see, like with your eyes. They make a lot more sense when you look at them, but the later ones are more accurate. So we need like the like understandability of the old ones with the functionality of the new ones. And that's going to be a challenge going forward, but it's going to be really cool.
Awesome. You have to send us the link when you get it done.
We will.
Okay. Well, thank you all so much, and hopefully
Thank
we'll
you.
stick around and answer questions afterwards.
Thank you.
Thanks.
Gotta get the microphone.
Just the sound goes into top, so if you just like you clip it in your pocket or something.
Presentation. Maybe it's easier to find it. Just a second. I think there's a presentation button.
on the desktop lower right corner? Drag these,
Oh no, I meant inside of Adobe. Is there a way to present? Maybe, are you familiar with how to make it come up in presenter mode?
No. Usually I use Google Slides.
Oh,
But,
Google Slides?
yeah.
Okay.
I wonder if you could.
How to make this into presenter mode.
Oh, hold on.
Okay, what is, oh,
Let's just drag it over.
well,
Worst,
there's
worst just
full screen. We could do
full
full
yeah.
screen.
That's
Yeah, but
probably
you want to get it on the other one.
Yeah, yeah. Well, so okay, that's
Just
good.
drag it over and then full
Yes.
screen.
Excellent. We can make that work. Okay, and then and there is full screen mode. Okay, and if we're really lucky, we are lucky.
Let's go.
Excellent. Oh, and you have a microphone. Okay,
Mhm.
good.
Okay, so my project is how amending Martian and lunar regolith with organic compost impacts plant growth. So the plants I actually used were spinach. So I have a picture of Popeye because I like spinach. Um, so the purpose of this project is with the new space age getting closer and closer, it's important to explore new ways of surviving in some of our solar system's more harsh environments. The purpose of this project is to observe the impacts of spinach plant growth rates in Martian and lunar regolith simulants that have been mixed with compost. The results can then be used to determine if regoliths could be a reliable source of farming on these celestial bodies. What makes this project different than projects done in the past? Throughout the past few years, there have been many experimentations regarding the growth of plants in both Martian and lunar regoliths. It has been a long-known fact that plants are capable of growing in both types of regoliths. In fact, last summer, if you visit the Houston Museum of Natural Science and saw the space exploration section, there's a good chance that you saw a collection of vials filled with lunar regolith simulants with tiny plants growing out of them. A key takeaway from these experiments, however, is that growing plants in these regoliths can be tedious and difficult. That is where my project comes into play. My experimentation shows the plants can be grown very easily in these regoliths if amended with the compost. So what exactly is Martian and lunar regolith? Martian and lunar regolith both have unique properties that can both harm and benefit plants. Martian regolith is a sandy basalt-based soil with lots of salt. Martian regolith also contains nutrients such as nitrogen, phosphorus, and potassium. Lunar regolith, on the other hand, is mostly an assortment of rock chips with smaller quantities of salt and potassium. What type of compost did I use? For this project, I used black cow manure. Black cow manure is an organic cow manure-based compost that is notorious for amending numerous vegetable gardens and flower beds. The compost has large quantities of bacteria, which is responsible for nitrogen fixation and the conversion of nutrients into a form more easily usable by plants. How did I get the Martian and lunar regoliths? Unfortunately, I did not have the opportunity to ride a spaceship to Mars and the Moon, so I had to resort to using simulants. NASA in the past has released detailed documentations of these regolith compositions, which have been used by external companies such as United Nuclear to create artificial regoliths that can be used for experimentation. How did I set up my experiment? For my experiment, I had 4 pots placed directly next to each other under 2 growth lights. 2 of the pots contained 600 grams of Martian and lunar regolith independently, while the other 2 had 400 grams of both regoliths with an additional amendment of 200 grams of organic compost. 2 baby spinach seeds were planted half an inch deep, 3 inches apart in each of the pots. Growth lights placed above were on for 14 hours every single day, and the pots were watered once every 2 days, with half a cup of water. What I hypothesized. After doing research into the impacts of compost on generic earth soils, I hypothesized that the amendment of the organic compost with Martian and lunar regolith would lead to a 15% increase in growth rates. Comparing spinach plants grown in these regoliths. In my experiment, after observing the two regoliths and their mixtures over a period of 6 weeks, I got 2 main key takeaways. Martian regolith on its own is perfectly capable of growing spinach without any assistance from a compost or fertilizer. However, once amended, there was a 30% increase in growth rates. Lunar regolith on its own was incapable of nurturing spinach plants from my methods, but once amended, it produced some of the healthiest and biggest plants out of all. Why was the compost so beneficial? Compost has various properties that can lead to a massive impact in qualities of the soil. Compost has large quantities of nitrogen, which is an essential component for plant growth. Compost also has a very frothy structure, which when mixed in with dense soils such as lunar regolith allows for plants to have more airflow and an increase in aeration. Last but not least, compost allows for soils to retain moisture for longer periods of time, ultimately leading to healthier plants. Could this be a practical method of growing vegetation? The short answer, in my opinion, is yes. Sending materials such as soil and fertilizer can be extremely costly. So the idea that you can just bring the seeds and use either human or livestock manure as a compost with the addition of the regoliths already on site is much more preferable. Knowing this, I think it is absolutely possible that we could see colonizers using similar methods. Thank you.
I had been given to understand that there was a problem with lunar soil in that there's heavy metal.
Oh, really?
Heavy metal concentrations, or
Is it iron?
Not iron,
Okay.
but more like titanium and aluminum and other metals,
Mhm.
which I tend to think of as heavy metals, and that they the seeds get started, but then they kind of choke off. There were some papers written last summer in conjunction with those little thimble-sized flower pots that they use in growing, and it was University of Florida, UCF, Professor Earl, you may want to look that up.
Okay.
But the plans got started, but then they kind of wimped out and they felt kind of yellowish. Look, used mustard seeds, Arabidopsis. And it seemed like there was something causing the plants, something in the soil that caused the plants to go off. So,
Yeah, that's interesting. So what I actually thought was the reason they didn't grow was because whenever the lunar regoliths mixed with water, it turned into like a hard, almost like cement-like material, and I hypothesized that that prevented the plants from actually sprouting, but that could possibly be a more liable reason.
well, the other notion, I think, hypothesis or conjecture was that the soil, the lunar soil, is fragmented. It's basically like busted glass.
Yeah.
And shards, and that after a certain point, the root system, the roots, it is so big that now they were jamming up against the rock shards and getting cut.
Oh.
And that was a mechanical reason for why the waves so
Yeah, that's really interesting. I'll look into that. Thank you for sharing that with me. Is that it?
No, you're saying Mars soil was pretty much able to support the growth. You went for what, 14 days, I think you said?
6 weeks.
Oh, 6 weeks. Okay, so you got pretty far along in the growth cycle. And so did you actually produce like a little spinach?
I didn't try eating it. There was small,
Which
like
is probably
small
a wise
leaves.
idea.
Yeah. There were small leaves. None of them, I don't think they got to a point where they were far enough in their development that you could actually eat them. So maybe if I don't have the plants anymore, but if I continued growing them, that's something I could have tried. But unfortunately, I didn't get to that.
Yeah, at some point, somebody's going to have to try it.
Yeah.
So the Martian soil in and of itself did not have a too high salt concentration. I look at Mars and I look at it, I think it used to have an ocean on it, but then the water evaporated. And when that happens on Earth, you end up with a place like the Salton Sea or the Dead Sea, places out in California, salt pans or Nevada, and that's what the soil is. And so it was hard to grow stuff outside of Salton Sea. The soil was. So you're saying that the salt level in these Martian simulants was not so high as the salt in the city.
I suppose so. The plants didn't seem to like be unhealthy at any point. They were, they did slow down a tiny bit in growth at the end, but like it didn't look like they were like hurting or anything. So that's interesting.
Well, that's great news. Very, very impressed.
Cool. And do you plan to do any follow-up experiments?
I'm still pretty indecisive of that. I think there's a lot of holes in my project that need to be patched up. Because like my sample size was very small, so it's possible that there could be outliers which could skew the results. And then additionally, maybe having it compared to a better control such as just earth soil. So I could see how I could build on this in future experiments, but as of right now, I'm not sure.
May I ask, where are you in your schooling?
I'm a freshman. I just entered high school.
Okay. All right. Very good.
Thank you.
You know, I'm sure your biology teacher next year will be really impressed
Thank you.
with this, and also encourage you to carry on and do more experiments. This is going to be, I mean, if we're ever going to get serious about living elsewhere on the surface of the earth, this is the key issue. Next to, right after breathing, having food is the next most important issue.
Absolutely, yes.
Well, thank you so much. Just want to
Of
present
course.
this to
Thank
you.
you.
And then let me go and get the microphone from you. No worries. Okay,
Thank you so much.
thank you. And next we have Japesh Banker. And also, did your partner, he didn't come, but I'll give you his award so that, and maybe what we could do is just move it further down here. And then I can give this to you. Thank you very much.
The project I conducted was a study on the impact of fins on model rocket flight in relation to altitude and velocity. Modern rocket technology has evolved over a long period of time, so why don't we go back in time to see how this all started. The first ever rocket technology was developed in Germany by a man named Wernher von Braun in 1929, and aimed to enhance the country's artillery power to aid them in World War II. Post-war, America brought in these German scientists to help out in the Cold War for the space race to get to the moon and with Russia. And along with rockets, what many people tend to forget is it's not only the engines or the main body that counts, it's the fins, because fins offer balance. Because without balance, the rocket will go in crazy directions. So to conduct this study, we took the 5 most common fin types, which include elliptical, trapezoidal, clip delta, tapered swept, as well as rectangular fins, to test which fin would perform the most optimal in model rockets. And what's really there's not enough data regarding how these fins impact the rockets, especially in small size rockets, because maybe in NASA industrial size rockets, there might be some data regarding that. For model rocketeers, there's not that much data in the dark. To conduct this experiment, we first started off by assembling this fins, which was a simple process of attaching the foam nose cone to the body tube. And we then prepared the balsa wood, which was the material that we used to create these fins. We coated this balsa wood with a protectant to ensure that there would be no abrasion or specks of dirt on top of these fins to ensure that this data was precise and accurate. And we then constructed these fins by constructing templates, which can be seen. I don't know if y'all would like to flip this around. So you can just start here and you can pass it in. Just flip through things. We created some templates that we glued down onto this wood to ensure that the old cuts were precise. And after these templates were made, we attached the fins by using a polar graph to ensure that these fins were distributed evenly across the body tube in 120-degree intervals. And we then launched these in a field to ensure the safety of people around us as well as ourselves. And we first started off by placing our pressurized launch pad, which was essentially a mini table, on top of the field to ensure there was a flat surface, to ensure that the flight was straight up. And since by regulations we were not allowed to use a engine or any sort of flammable material, we had to use a pressurized air launcher, which ensures why the bottom was a hole. And we did 3 to 5 trials with a pressure launching at a pressure of about 60 psi or 4.14 bars roughly. And we then got the times that the rockets took to reach the apogee. And these times were then plugged in into the displacement formula and the acceleration formula to find out, one, what their apogee was, and two, their initial velocity and how long it took to take that apogee. And it was found out after calculating all of these values that the elliptical fin performed the best due to its curved structure, which would help it reduce induced drag. And some notable values for the elliptical fin was about 17.64 meters for its apogee and 18.37 meters per second. And which brings our elliptical fin to be performing the best. This could apply outside to other beginner rocketeers who are confused about what fin they should use, right? Because even though we took the 5 most common fins, there are about 100 fins that are out there, some that are just created by luck, some created just essentially for the use of rockets as well. And it could also help out with other industrial size organizations too, because our insights could be incorporated into the rockets from our small rockets to their massive rockets as well. Any questions?
So these results really were applied to this velocity range and this acceleration.
Yes, sir.
Like change as you increase the velocity.
Yes, sir.
And you said that you're not allowed to use.
No, sir.
Is that
So this was obviously a science fair project as well. So with the ISEF regulations, they do not want anything flammable, whether it's just a little smoke or whatever, which is yes, sir. And yeah, so we were drawn to setbacks as well, as balsa wood's not very durable, even though it's very lightweight and tends to break as often. And using an air launcher, we could not achieve a very great height. And we couldn't use a parachute either, as the parachute, so a parachute would help slow down its downward fall. But the problem with that was we had to incorporate an altimeter, which is what we were initially going to use before using calculations to find these values. But the problem with the altimeter is it recognizes the launch and based off the jolt from the engine knocking it all the way up. But the problem with that was there was no engine. So even though we initially started with an altimeter, the altimeter was not collecting data. And without the altimeter collecting data, the parachute would not initiate, which would not slow down the fall, which also contributed to the rocket not being as durable. But luckily, there was no damage to the rockets done until after all the experimentation was finished.
So my question was, have you ever thought about modeling and coming up with sort of an equation, say like whether you have this shape, this area, instead of those? Based on that, could you come up with a formula for how well?
We probably could in the future, which initiates why we do future testing as well, as maybe we could try it on larger rockets, as due to supply chains, we cannot essentially use a bigger rocket without using a engine, because the bigger the rocket, the more space there is. And I'm not sure you all can see this model very clearly, but with a mini tube to facilitate the air pressure inside to launch the rocket in, it would need a smaller area unless we would use an engine. We did try to regulate and keep everything as constant as possible, including the weather conditions, as these were all launched in a consecutive period of about an hour. Each rocket launched in the same weather conditions and same wind resistance as well. All these materials were all made out of the same material as well. Maybe a plastic body tube, foam nose cone, balsa wood fins, and at the same PSI as well. With further experimentation as well, we could probably launch these rockets in warmer temperatures as well, as with warmer temperatures, there's moist air, which would provide more drag against these fins, which might change the results as well. But given the current weather conditions that these rockets were tested in for fire trials, it was found that the elliptical fin. As well, elliptical fins are not seen outside as well, because given its curved structure, it's extremely difficult to incorporate in other rockets, especially if you're manually cutting them, because we manually cut these elliptical fins as well, and probably with more advanced laser cutters that exist as of now to cut sheet metal or whatever material is used inside industrial sized rockets. Those could probably be improved, making.
So the leading edges of the level.
Yes, yes. So
Started out with rectangular
yes, sir.
stock, I assume, or
Yes, sir.
90-degree edges.
Yes, sir. Yes, sir. So we use templates for these, and this brings us to how we attach these as well, that I forgot to mention. We made sure that the wood grain that we used was perpendicular to the rocket fin, as parallel wood grain would do that.
Oh, yeah.
Do you have any further questions?
I guess one I'd like to ask is, do you plan any follow-up research?
Yes. So maybe when I get more time as well as the school year ends, I'll put in more time to this project as well and find maybe larger rockets as well to greater test and incorporate engines, since it's not going to be for a science fair project. I can find other data to help support which Finn will work with us as well.
Since that won't be part of a science fair project, do you plan to use engines at that point?
Yes, sir. Yeah, I'm going to plan to use engines because engines are cool and they would probably provide much more valuable data, as air is not really optimal for people trying to launch into space. Thank you so much. Yes, sir.
Given the manual and the service on that app, with the data that you collect, and maybe perhaps even the equation, be able to be input into their application to create some form of simulation.
Yes, I believe so. I'm not sure yet, but given what they've used for their simulation, I would assume that they would.
I say, send each other's gamer tags and
Yes, sir.
talk about it. While
Yes, sir. Of course. So we could probably CAD these out using computer-aided design, just to like put the fins on a broader scale that we can then insert into a simulation to see how it would work with mathematical.
I was thinking if you guys work together with the model of the model how we create rotational inertia. That might be some sort of way to model high velocity.
Of course. You have any more? Thank you so much for your time, guys. Really appreciate it.
So I wanted to give you this, maybe give the other one to your partner.
Yes,
That'd
sir.
be great.
Thank you so much.
Congratulations. And could you help me with this?
Yes, sir.
Or I guess I'll let you move it. So we have two more presenters that couldn't be here with us in person, but they're online. Before we move on to them, is there anybody here that I may have missed? That was everybody that emailed me. So I just thought I mention that. Okay, good deal.
What are the two titles?
Yes, so we're going to have creating a man-made biological leaf that can perform photosynthesis more efficiently. Let's see, and this is by Danny. Danny, are you online?
Yes, I am.
Danny, could you say something again?
I'm
Oh, yes, thank you. Okay, there you are. And let's see, spotlight. And did you have something you wanted to present? If so, I'll make you a co-host.
yes, I do.
Okay, sounds good. Let's see. And maybe I have to do that from the other one since, hold on just a second. Okay. Make co-host. Yes. Excellent. And I'll just put you up there. Okay. Okay. So everybody is seeing you online. Go ahead and present, and we'll go from there.
Okay.
Wonder.
So, okay. I made my project of creating a man-made biological leaf that could perform photosynthesis at a more efficient rate. My project was about how plants currently, they can only use about 2 to 3% of the absorbed light energy that they consume to release oxygen that can be used outside of the cell. This has worked for centuries, but with the increased demand of resources that humans have used and the amount of pollution that we've released into the environment, we need a better and more efficient way to provide oxygen for our environment. So my artificial leaf mimics the conversion of sunlight into chemical energy and into oxygen that can be used outside of the cell. Before I did my project, I did create my hypotheses, and it was whether or not the leaves that I created would survive, and also if they would be able to actually perform photosynthesis at a more efficient rate. Throughout the project, I used natural resources that were naturally occurring and as cheap as possible so that my project could be as accessible as possible. So for my base, I used a spinach leaf, and for my chloroplast, I used spinach chloroplasts that were already existing. So for the first procedure, there was 3 procedures in total. I had to create my base for the plant. To do this, I trimmed down the leaves. I cleaned them so that there wouldn't be any outside influence, or it would just be the plant. And I decellularized the plant to leave just the scaffold behind, the scaffold protein. I did this by applying an enzyme solution to break down the cell walls on the plant cells. And I used a bleach solution, a detergent solution, to decellularize what was remaining of the plant life. So I allowed the leaves to incubate in that solution for several days. You can see the SDS solution, which is the enzyme solution that I first applied to it. And this destabilized the cell walls and also broke them down. And you can see the final result that I had at that point, which was the plants with broken down cell walls. And then I immersed it in, this is the final part after the enzyme solution. So it was slightly clearer, but it lost most of its rigidity from the cell walls. And then I put them in my detergent solution, which slowly decellularized the rest of the plant, removing all remaining life. And I had to wash off the detergent from the plants so that it wouldn't continue to kill off any life. And in that process, I did manage to mess up the structure of the original plant, but it was still able to hold life. It was just slightly less aesthetic. So that was the first part, isolating the protein scaffold. For my second procedure, I had to isolate the chloroplast from a existing spinach leaf. And to do this, I treated the leaves with the same enzyme solution that I did at the first place to break down the cell walls. so that I could access the chloroplasts within the cell walls and within the cell membrane. But after this, I applied a sucrose solution so that the chloroplast membrane could be strengthened, and I grinded it down in a mortar and pestle so that it could be accessed through simple filter through a cheesecloth, the chloroplasts. So here after applying the sucrose solution, I grinded it down in my mortar and pestle. And what you can see in the right side, the rightmost picture is the isolated chloroplasts after. For procedure 3, I only cultured the protein scaffold in the chloroplasts that I isolated together in a petri dish. I allowed the cells to culture under a UV light for sterilization. And in the second photo, you can see me actually applying the chloroplast to my scaffold. And here you can see my plants after they were cultured. So for my results, this is the end product. All 5 cases that I experimented on were able to sustain life for upwards of 2 weeks, which is actually a very successful project, as the project that I modeled it after an existing project that was very expensive. It was not very ethical because it used animal parts to create it. So it used silk moth cocoons, and that caused them to die. So it was not very ethical. It was very expensive. It was a very lengthy process. It took upwards of 3 months, while my project took less than 3 weeks to perform completely. And my plants were able to survive upwards of 3 weeks minimum, when the project that I modeled my experiment after was only able to survive for a couple of days. So this leaf could be used in spice exploration as an oxygen generator. Its advantage over regular plants is that it doesn't require soil or any special nutrients, and it isn't confined to problems that plants might face in zero gravity. So it does not need to grow outwards. It does not need anything other than carbon dioxide, and it doesn't need anything other than carbon dioxide and photons, which is just light, to perform photosynthesis and release oxygen. And that could be used in space theoretically. So there's also other applications that this could be used on Earth. It can be used in buildings, day-to-day life. It can be used for bioremediation and environmental conservation, along with other things. So yeah, for my conclusion, upon successful implementation, the biological leaf was expected to exhibit enhanced photosynthetic efficiency. It was able to perform photosynthesis, and it was able to release oxygen into the air. And it would pave the way for creation of bioengineered systems in various fields, such as biotechnology, environmental conservation, and space technology. So, thank you.
Thank you, Danny. I think I can turn this around so you can actually see the audience. Can you see the audience?
Yes, I can.
Excellent. So does anybody have any questions? Okay.
So, have you tried simulating this in like a vacuum setting? Like, would you think about doing that in the future? Like, if you're in
Yeah.
space and you don't have oxygen already in the environment?
So what I'm I still have plants that the original 5 petri dishes that I had at the beginning, at the end of my experiment, they did die after a certain period of time, but it was a very extended period of time. So I'm going to re-perform the experiment under different conditions, since all of my case studies were successful. So yes, I would reperform it under a vacuum to replicate space conditions.
Yeah, great work. Keep it up.
And you had a question too?
Were you able to, I'm very impressed with you taking your experiment and looking for other applications. Did you talk to anyone within those industries about your ideas to get their feedback?
At the fair, I was able to talk to people in many different. There was actually one man, his name was Tim, and he was able to help me expand more on different applications. One of
Okay.
where was actually um, was actually was actually like using it within environments that were affected by CO2 pollution and the carbon pollution. So he encouraged me to continue to research my project in that field where like environments that have been overly polluted, even underwater. So yeah.
Okay. Excellent. Thank you.
So anybody else have any questions? Well, thank you so much. Oh, go ahead.
Yeah. What do you think the maximum lifetime would be for these synthetic leaves?
So for a normal leaf, it usually wouldn't be able to survive over a week. And in the experiment that I modeled my experiment after, it was not able to survive for more than a couple of days. My experiment that I performed for the first time was able to survive for upwards of 2 weeks. So I think with further research, it could be able to survive for um, more than that, for almost a month, even months, if we could really refine the process and do further research. Yeah.
Yeah, that seems like a good direction to go to figure out how to make that process last longer.
Yeah. And by doing that, I would also to continue to explore how to use this space over long periods and long future.
Well, thank you so much, Danny, for being able to support this through Zoom. And it was a really interesting project. And we have one more presenter online. And as soon as I find my mouse, we can is out. Okay. The next one is testing ionic wind as a form of aircraft propulsion by Ajefo. Did I get that close? Maybe not. But can you hear us? Let's see. There we go. Ajefo, can you hear us? Yeah, that's probably the right button. And then oh, you can't unmute yourself. That's interesting. You should be able to remove unmute yourself. So I'm clicking the ask to unmute. Could you? I'll try reconnecting. Okay, that's a good idea. And while she's reconnecting, is there anybody else online that I may have missed? Thank you, Robin. Okay. Hey, got video. Any luck? Eh, yeah. People should allow participants to unmute themselves is checked. So that's there. I tell you what, I have this mute participants upon entry, so I'll uncheck that. And if you're unable to mute yourself, just try disconnecting or reconnecting, and that should take care of it this time around. The best I could do is to click on ask to unmute, because you can't just, privacy thing. You don't want people unmuting you on a conference call. Okay. Well, while we're waiting, I got a couple of questions. Oh, yeah, I could do that too. I'll have to if she presents. Okay. Never. Okay. Uh-huh. Oh, still came in as muted despite that. Okay, well, I'm going to make you a co-host. Oh, I can't do that from there because, oh, that's interesting.
Oh, I'm sorry. Figured it out. Can you hear me?
Oh, excellent. Yes, we can hear you. This is brilliant.
Okay, that's great.
Welcome.
Thank you.
We'll put this over here. And did you have did you have something to present?
Yes, definitely. I'll have a little slideshow prepared for you guys.
Okay, let me go ahead
So,
and still make you a co-host, as that will be necessary. There you go. Oops, nope, not quite yet. Okay, how about now? You should be able to share out. Then
okay, so
excellent.
my project was testing ionic wind propulsion as a form of transportation, or testing ionic wind as a form of aircraft propulsion. Starting with the rationale behind my project. So in today's transportation industry, we look for a few key factors such as efficiency, environmental stability, sustainability, scalability, versatility, so on and so forth. Now, ionic wind can meet all of these demands and more. It's a form of propulsion that's already been tested by organizations such as the Massachusetts Institute of Technology and NASA in past experiments. I want to say around the early thousands or before the 2020s decade. So I decided to take inspiration from their experiments and make something that was my own. Now, moving on to my driving question. How efficient is an ionic wind thruster in terms of input divided by output? Depending on
Um,
this efficiency,
can I
would
interrupt you just for a second? Would it be possible for you to put on your video?
um it should be on.
Oh, it should be on.
Is it? No.
Not. Uh, I mean, we see the presentation, but we don't see you.
Oh. Um
Oh, there we go. Oh, you popped up there for a second. There you go.
sorry. Is this better?
Okay, excellent. Yes.
Thank you.
Yes.
Sorry.
That's perfect.
Moving
Okay,
on to
thank
my
you.
driving question. Moving on to my driving question. How efficient is ionic wind thruster in terms of input, in terms of output divided by input? And depending on this efficiency, does it have potential as a form of transport? So in this experiment, I hypothesized in this experiment, my goal, in terms of an engineering goal, was to test the efficiency of ionic wind propulsion by constructing a small aircraft or thruster and seeing if it can support a load, let alone its own weight. Now, I hypothesized that it would be able to support its own weight as well as additional weight. If this goal was met, then it would prove that it has potential as a form of propulsion and transport. Now, moving on to some context. Obviously, you're probably wondering what ionic wind is, and it's a phenomenon based on corona discharge. Now, corona in the individual sense is charged particles such as electrons and ions that are being affected by a nearby electric field. These charged particles engage in a series of collisions that create more ions. Corona discharge is corona that's produced near small edges or surfaces, such as wires with a small diameter or sharp needles. Now, ionic wind uses corona discharge in a specific way, and it's corona discharge that is produced near by a pair of electrodes. So the positive electrode, or the anode, I'm pretty sure, produces corona discharge that moves towards the cathode, and this corona creates collisions with other neutral air molecules on its way down to complete the electrode, creating a neutral wind that can produce thrust. Here's a diagram of such type of thruster. So here you can see the thin wire that would produce the corona discharge, and the electrode, the lower part of the electrode, in this case aluminum foil, that produces a circuit in the form of an electrode that produces thrust moving down from the upper electrode to the lower electrode, producing an equal and opposite reaction that makes thrust that pushes the electrode up. So I used a 6-volt industrial battery, a 3x300 by 300 millimeter piece of phenolic board, 6-volt to 20 kilovolt transformers, 1-pound weights, aluminum foil, plywood sheets, wooden dowel pins, and 42 gauge copper wire. For my procedure, I constructed the frame for the thruster using the dowel pins, using the wooden dowel pins, including a space for the battery, copper wire, aluminum foil, and the wiring. I threaded the frame with the copper wire, constructing the upper part of the electrode, and then I lined the frame with the aluminum foil, creating the lower part of the electrode, and I secured the battery and transformer. I began assembling the circuit, connecting the upper part of the I'm sorry. I began constructing the circuit, wiring the upper part of the electrode to the, I guess you can say, positive side of the transformer, and constructing and connecting the negative side of the transformer to the lower end of the electrode. I didn't connect it to the power source until I was ready to begin conducting my experiment, and I used a multimeter to ensure that all components were properly connected. So after connecting the battery to the transformer and beginning the experiment, I first tried to see if the thruster could hold its own weight in the air, and then I began incrementally adding 1-pound weights until the thruster could no longer support the load. Here's a few pictures. My thruster supporting its own weight and the weight of about 4-5 pounds. Now, in addition to its own weight, my thruster was capable of carrying 10 pounds. So there's a series of calculations that I used to get an efficiency percentage that quantifies how much energy was put into the thruster and how much it was able to transform and release in a quantifiable form. So it had an impulse of 6 volts, and the battery had an estimated amperage of about 1 amps. Multiplying volts by amps gives 6 volt amperes, which is equivalent to 6 watts. Multiplying that by the time in hours that my thruster was active, or 0.0166667, which is about 1 minute, gives 0.0.100000002 watt hours, which is the input. The output, 10 pounds, which was the weight carried by the thruster, is equal to 10-pound force. Multiplying that by 4.44822, a value of 44.4822 newtons can be calculated. Now, to convert newtons into joules, I would have to multiply the energy in newtons by the distance traveled in meters. And I gave my thruster a space of about 6 inches to lift into the air so I could maintain a control over it. So that's a distance of about 0.1524 meters. So multiplying that by 44.4822 a value of, I'm going around and say 6.779 joules was produced. Now, using an online calculator that divided the input in watt hours, that divided the output in joules by the input in watt hours, I got an efficiency rating of 1.883%. Now, this efficiency percentage honestly shocked me quite a bit. I was expecting an efficiency percentage of about 65%. And I suppose where I lost this efficiency was the amount of distance that thruster traveled in the air. Perhaps if I let it travel about a full meter or maybe 1 foot while carrying the 10 pounds, I would have gotten a higher percentage. But I digress. So moving on, again, like I said earlier, most modern transport systems are centered around fossil fuels, which eventually will run out and have negative impacts on the environment, which is why it's so important that as a society, we find environmentally friendly forms of transport. In this case, ionic wind propulsion. With this, we could lower CO2 emissions and work towards restoring our environment. In the future, if I were to continue working on this project again, I would probably work on factors such as achieving a higher efficiency percentage, making a more compact or larger thruster to test the factors of scalability, and finding different ways to construct thrusters using different components or different forms of components, such as thinner wires, lighter materials, etc., etc. So in conclusion, my project went over corona discharge and its use in ionic wind. And I constructed, tested, and compared a thruster to organizations like MIT, to a thruster made by organizations like MIT or NASA. And my hypothesis that ionic wind was a viable form of propulsion was incorrect, because the thruster had a 1.883% efficiency, which is relatively low compared to about 65% efficiency that you would see from a vehicle such as a car. Now, although I did receive a relatively low efficiency percentage, my thruster was able to carry about its own weight times 9 or 10, which I believe is still a good result for only 6 volts of input. But it still did not receive the desired efficiency percentage, so my hypothesis was incorrect. Any questions, comments?
Okay, go ahead.
First of all, congratulations. I tried to build one of these about 20 years ago and it wouldn't even pick up its own weight. So that impresses the dickens out of me. Secondly, the notion of using the ionic wind as the sole or principal form of propulsion is a great goal, but maybe there might be some utility to using this as a add-on to existing wings or airfoils. Seeing about, I mean, there are historic options of blowing or sucking air out along the leading edge of a wing and sucking it out somewhere out the boundary layer, trying to squeeze out 1 or 2% more efficiency on the aircraft's flight, and perhaps using ionic wind augmentation on a wing might prove to be a valuable thing. I think that if you can get, I think a 0.5% efficiency improvement in a wing on an aircraft, that all the aerodynamics folks basically just do handsprings over that. So this might be a very viable phenomenon to continue looking at.
Noted. The reason I tested it only as its own form of propulsion was adding it on to another form, at least right now, wouldn't give me a very good estimate of how much well, how good it does on its own or how efficient it is on its own, which is what I was
True.
really trying to. And I do know that this form of propulsion is similar to how ion thrusters in space work, but instead of the molecules or chemicals that we have in our atmosphere, such as oxygen or nitrogen, they use external fuel sources, such as I think butane was one of them. But yeah, I do know. That is a good idea. I will keep that in mind for the future.
Yes,
Thank you.
don't throw it away just because it couldn't be used as a sole method of propulsion. I mean, it still has notably positive benefits as a possibly as an add-on. So very good.
And let's see, Greg also has a question.
Yeah, I was just curious on some details. You're starting with low voltage DC, you end up with 40 kilovolts DC going through. There's a transformer in there, which would be an alternating current kind of device. You probably had some way you chopped it or converted to AC along the way.
Yes, I did manage. I did I did facilitate the transformation from AC to DC, but my transformer wasn't 40 kilovolts, it was 20. The diagram was just an example.
Okay, but I just meant in your list of materials, you didn't include the electronics you would need to actually use the transformer. I assume you built the transformer. You had that 42 gauge wire.
Oh no. The transformer was externally sourced. I don't know much about the internals, but yeah, but I did wire the battery to the transformer and it was able to work
Oh,
properly.
okay.
I'm assuming that there was already something to facilitate that transformation inside the transformer because it
Okay,
was already
thanks.
pre-made. I didn't assemble it myself. No.
Excellent. Thank you. Any other questions? Well, very good. Thank you so much for presenting. Go ahead and see, move that. Oh, actually, this, well, okay. So several things. One is, how many people know when was the last time we had people walking on the moon? Can you raise your hand? What year we had somebody? Somebody walking on the moon. Okay. What year was it? Excellent. And when's the next year we're going to have people walking on the moon again? 2026. Excellent. And I don't have another patch. And is there anybody here that wants to become an astronaut? Well, you should apply before April 1st.
That's right.
Because applications are open. Now's the time. But you're the only one that wants to be an astronaut in this entire room of space people. Okay. Well, these are the people that you should kind of research. The current NASA astronauts. Okay. So before we all go, I was going to have everybody online turn on their cameras and get everybody to stand up here and take a group picture real quick. But I also want to let y'all know that y'all are welcome to join us at PJ's Coffee. It's right down the street. It's literally 0.4 miles away, and just a chance to hang out. We got approved to do a community outreach booth at Comic Palooza, so it'll be a good chance to kind of talk about some ideas about what we want to do with that. And just get to know each other a little bit better. So with that, if I could get everybody online to just turn on your cameras, and if I could get everybody here in the room to just stand maybe not directly in front of the people. If you wouldn't mind, Greg, oh sorry, wouldn't mind, Doug, just let me, so I need to figure out how to unspotlight. Nope. No. there's got to be another view, okay, that's that. Oh, okay, almost. Okay, getting closer. Yes, we did it. Technology. Okay, and if I could just get everybody to stand up there in front, and I could just grab a quick group picture, that would be fantastic.
You want to get in it? I can take the picture.
Oh, you're sure you don't want to be in it?
Well, I'm just visiting.
Oh, well,
Just a second.
okay, sure thing. And we could just, if we could just get everybody kind of up there, that'd be brilliant. Thank you so much. I really appreciate that.
Go ahead and get in the picture with your camera.
Yeah. Excellent. Glad you're able to come.
I got the picture.
I think you guys need to come in a little closer.
Okay. A little.
A little bit sideways, and also maybe the second row.
How about the kids in front?
Kids in front. Yeah, maybe we can put all the kids in front. Yeah, and then I'll just scoot back here. Yeah. Okay. How's that? And you could just.
Always move for the astronauts.
Let's put the presenters in chairs in front. Presenters, grab a chair.
Sitting down or something.
Technically in the picture. Why?
I don't mean
that in a bad way.
Have you been?
Come on.
There we go. Okay. How are we now? Do we need to squeeze even?
Sit there.
Okay.
Okay, I love that.
Okay. Yeah, no, you're. Oh, I'll just get right here. I'm good.
Everyone smiling. That chair in front of your with your hand. One, two, three. One, two, three.
Okay. Thank you all very much. Well, I'll go ahead and end the online meeting. Thank you all so much for joining us online, and thank you for everything. And we'll be in touch. Okay. Take care.